Hi, welcome everybody. In this fifth session, we will discuss in particular on two systems in dynamic model, first and second order systems. Okay, in the previous topics, we have already discussed about the general expression of a transfer function, as you can see in this slide. So transfer function normally is always represented by the fractional form of a polynomial of S, where in this case the numerator has an order of m and the denominator has order of n. We also discussed last time that any higher order polynomial of S in this case, we can always be able to factorize it into a combination of first order or second order equation. So in this example, again, the numerator, we factorize it into this form, right? That contains a first order polynomial with m factor from s plus z1 all the way until s plus zm. And then in the denominator, we can also do the same thing. But we discussed also in the past that the pole of transfer function not necessarily to be a real number. It can be also a complex number. But if you have a complex number, this pole will not appear alone. It will always be accompanied by the conjugate of that complex number. Let's take an example of this case. So let's consider we have a system where the transfer function looks like this. If you look at it, the numerator has a polynomial of 2, the denominator has a polynomial of 4. If I factorize both of them, the numerator as well as the denominator, I will get this form. It might not be easy to do it by hand, but you can factorize it easily if you have a good calculator or MATLAB in front of you. Let's just not bother too much on how to factorize it. I have factorized it already for you. So this is the factorized form of the transfer function. Now let's take a look what I'm going to do. For this part, the one that contains complex poles, I will expand it. So I will multiply these two forms. If I do that, I will get this form. So this part basically is the multiplication of this part. Okay. So now this is the form that of the transfer function. If you look at this, there are two forms of polynomials on the denominator. So what I'm going to do now, I will do a partial fraction expansion. You still remember about partial fraction expansion, don't you? This is the way that we normally do when we are going to do a Laplace transform operation. If I do partial fraction expansion to this transfer function, I will get this form. If you look at this, the first term here on the denominator has first order polynomial. What I mean by first order polynomial, the highest order on the denominator is 1 here. Okay, so the first term has a first order polynomial on the denominator. If you look at the last term, the highest order of the polynomial on the denominator is 2. So this I call it as a second order polynomial. This is first order. What about the middle one? If you look at this, of course, if you evaluate this expression, this will also be a second order polynomial. Okay. So what do I want to say here? What I want to say here, any high order system, any form of transfer function, it doesn't have to be first order or second order. you always be able to decompose it. You will always be able to rewrite it into a combination of first order and second order. Any kind of transfer function. Okay? So as what I just mentioned, higher order system, what I meant by higher order system is a transfer function with any order of polynomial on the numerator as well as on the denominator, can always be expanded as a combination of first order and second order. Just like what we did before. We have first order here and second order on this. Any higher order systems on your transfer function, you can always be able to factorize it into a combination of first and second order systems. Okay, so if you can factorize any higher order system into a combination of first and second order system, the system response, if you want to evaluate it, will also be a summation of the response of each of these factorized form. Okay, now let's take a look again the transfer function that we just evaluate. This is the transfer function that we have, and then after we partial fraction expansion it, it is becoming like this. It's a combination of first order and second order systems. Now, what we can conclude from this? Any higher order system can always be factorized into a combination of first order and second order system. What is the nice thing of this? When we are dealing with a mechanical system, not necessarily mechanical system, but any system in nature, most likely you will deal with high order system. It can be 4th order, 5th order, 10th order, 100th order, or even 1,000, 10,000 order system. Then that will make your analysis becoming more complex. But thanks to this fact that any higher order system can always be factorized into combination of first order and second order system, because of this fact, we don't need to study any higher order system. We don't need to study 3rd order, 4th order, 10th order, 100th order, 1,000 orders. We just need to study first order and second order system, because essentially any higher order system can always be represented by a combination of first order and second order system. So this is the motivation why we, in the next 2 topics, only discuss first order and second order system. Okay, so let's move to the next pit stop. In the previous topic, we were discussing route stability. Now we are moving to the first order system. And then later on, we are going to discuss a second order system. Once we discuss these two, we should be able to analyze any higher order system. Let's start with the first order system. In general, first order system can be represented by this differential equation. Okay? Or I can also rewrite this differential equation to this form, where again R is the input to your system, C is the output of your system. And in this case, we have 2 parameters here, T and K. If you look again at the differential equation, this equation involves only the first derivative of the output. So clearly, it is a first order system with 2 parameters, T, where T, we call it as a time constant, and K is the DC gain. So if you have a first order system, you always have 2 parameters on your first order system, time constant, T, and DC gain, K. We can represent the dynamic properties, the differential equation that represent the property of the first order system into a transfer function form. You know how to convert differential equation to a transfer function. We discussed it already in a very first topic. So You can try it also by yourself. So what you see here in this slide is the same system where the transfer function is represented in transfer function form. The behavior of the system is represented in transfer function form. The ratio between output and input in Laplace domain. The ratio between C and R in Laplace domain. So clearly, as you can see in this slide, there are two parameters, K, which is the DC gain, and T is the time constant. In terms of pole zero pattern, I can rewrite this transfer function into this form. You know how to do this. I just divide both sides, the numerator as well as the denominator, by t. So once I have this form, you can identify the pole of the system. You still remember what is the definition of pole? Pole is the value of S that will make your transfer function equal to infinity. So if you look at this form, if I change my S, if I substitute negative 1 over t to my S here, the denominator will become 0. So my C over R will become infinite. So in this case, then 1 minus 1 over t is the pole of this transfer function, right? So if you have this first order system, the pole of your system is minus 1 over t. Okay, so for the third representation of a dynamic system, as what we discussed last time also, there are three ways: differential equation, transfer function, and the last one is block diagram. And block diagram is nothing more as a pictorial representation of a transfer function. We can draw the block diagram of our first order system into this form, where in this case R is the input, C is the output, and the transfer function is written inside this box. Okay, and then as another example, this block diagram that you see on the right side is the equivalent of this block diagram, the one in the left, only in the case when your DC gain K is equal to 1. So these two are equivalent to each other. As what we discussed also in the previous slide, as another alternative of this block diagram representation, you can also see the one on the right side here. Basically, this is also another representation of this block diagram, but this is in particular when the DC gain K is equal to 1. You can also draw it like this one, right? And then in the previous slide, we have also discussed that for this particular system, the pole of this system will be equal to negative 1 over t. If you want to represent this pole location in S-plane, you can draw it like this one. So the pole is a real number for any real value of t. And if t is positive, of course, the pole negative 1 over t will be a negative value. That's why you can draw it somewhere here. Okay, so this is a pictorial representation of your pole of your first order system in S-plane. As a real example of a system that has first order property is an electrical system, RC circuit, resistor capacitor circuit. When you give a voltage input to these two poles, where the voltage is equal to EI, on these 2 points, you will get a voltage output which is equal to E0. And the relationship between E0 and EI is represented as a first order system like this, where in this case R is the resistance and C is the capacitance of this circuit. So as you can see clearly that this transfer function has a first order dynamic of the system. How? It's because the highest polynomial on the denominator is equal to 1. Another example of a first order system is an electric motor. So imagine you have a DC motor. How do you run a DC motor? You just pump in a voltage to the DC motor, and then the shaft of the DC motor will rotate. The voltage that you give to the DC motor, let's call it EA. EA is the input that you give to the DC motor because you are pumping a voltage to the DC motor. And the DC motor will respond by the rotation of the shaft. So the output of the DC motor is the angular velocity, the speed of the rotation of the shaft. EA is the voltage that you give as an input. Omega is the angular velocity of the shaft as an output of the DC motor. The dynamic behavior of this electric motor, of this DC motor, if you find the relationship between the velocity of the shaft and the voltage that you give to the DC motor, will be like this. It is clearly seen also that this DC motor has a first order polynomial in the denominator, which means you have first order system in here.